Okay guys, in this video lesson we're going to get into the next major term in this unit, which is energy. Okay, so we've already talked about work and what work is, so now let's go down the road of what is energy. Okay, so for energy, it really is very similar to work. In fact, we use similar units and the math kind of works out similar to it for it also. But once we start saying things have the ability to do work, okay, so work is the action, right? You're doing work on something. Well, what gives you that ability? So why can you provide a force over a distance? Well, it's because you have to expend energy, okay? So if you have enough energy, that gives you the ability to accomplish work, which is applying forces over a direction, okay? So if you look at it, it wouldn't be surprising that the unit that we use is the joule, which is the same unit that we use in work, okay? The thing is, we're going to find another way to calculate this by using energy instead of just work, right? That means we got to have energy to do work. Okay? It is often we interchange them. So we actually will talk at the end of this unit about a theorem called the work-energy theorem, which is going to allow this interchange between work and energy. Okay. Now, there are lots of types of energy. Okay. Energy is a little bit more abstract in terms of, instead of being like mass, or weight or velocity that we've been talking about, because energy is not something that we can see normally unless it's like light energy. But things that are considered energy in our world, okay, we have kinetic energy, we have potential energy, we have solar energy, we have electromagnetic energy, we have chemical energy, we have heat energy, we have light energy, we have sound energy, okay. In fact, we will touch on all of these different types of energies as we go through this year and how they work. So it doesn't really matter what we're dealing with in energies. There's all these different types. Now, these last ones, the solar, electromagnetic, chemical, heat, light, and sound, there's specific types of those that come from different sources. The kinetic and potential are very generic terms we use that deal with the types of energy. So we'll spend some time in this video lesson on what is kinetic energy versus what is potential energy. All right? In the world of mechanical energy, okay, so when you have things that has energy due to motion or your location, okay, we glump those two things together, the kinetic and potential, under mechanical energy. So this is energy comes because things are moving or because of your position in a location, all right? If you are moving, that's kinetic, all right? So anytime we have things moving, it's kinetic. Anytime it's potential, we have it stored, okay? I always think back to like when I was a kid in high school. I had one of my teachers once said, he looked at me and says, "You know, Kevin," he goes, "you have a lot of potential." And at first I thought that was a compliment, but usually what happened after that is the next word was "but," okay, and he was definitely going down the "but" world with me. So he said, "Hey, you have a lot of potential, but," and then he went on to describe the fact that I was super unorganized, and I basically, if I couldn't get myself organized, I was going to really struggle, which was really true. Because potential is this stored energy or this ability to do energy, but you're not using it yet, okay? So we get potential energy in lots of different ways, but they always come because of a position that we put something in or some sort of strain or stretch that we put onto something, okay? So think about like springs or rubber bands. If you pull a rubber band back, you're giving it potential energy, okay? You're using, chemical energy from your body and your muscles to convert that into potential energy for that rubber band. But when you hold it back, that's now all potential. It has the potential to be released and go somewhere. Now, position, usually we think of things in terms of height, okay? So if you lift, a really heavy object and store it on the top shelf in your closet, that has the potential to fall on your head and hurt you. So because of that high position, you now have potential for that, okay? Let's focus in just on kinetic energy now. All right. So with just kinetic energy, we're talking about that moving energy, right? So what's going on there? Well, if it's moving, velocity is definitely going to be a big part of that world of kinetic energy. Or how do we calculate how much kinetic energy is available? Then that's allow us to do work on things. Okay. So the first thing is velocity. The faster you move something, the more energy it has. Okay. So velocity is one of our big pieces here. It's actually the biggest piece of our puzzle is velocity. Now, the mass is the second piece of the puzzle. So if you have kinetic energy, that means you are moving and you have mass, okay? So things with kinetic energy have velocity and they have mass in them, okay? Which means the more massive you are, the more work you can do, so you have more energy, all right? So things that have the most kinetic energy are big things that move fast, All right. It's possible to be very, very big and have lots of mass, but be moving pretty slow, so you don't have a lot of kinetic energy. Or you could be very, very, very small and be moving very, very fast, so you have, again, not a lot of kinetic energy. So you need both to have lots of kinetic energy. All right. Put those two things together and we get the equation for kinetic energy. So if we're going to solve for kinetic energy, or the ability to do work based off of your movement and your velocity, okay, so remember, kinetic energy is a type of energy which is the ability to do work. So if you have a speed, and we're going to square that and take it times your mass, and we do 1/2 of that, okay, that gives us our kinetic energy in times here. All right. Labels. Kinetic energy is going to be in joules. Mass is in kilograms, and velocity is in meters per second. So a joule is a kilogram times meters squared per second squared, because we're squaring these values here. Okay, so that's what a joule really is. It's a kilogram meters squared per second squared in this thing. All right. So let's say you're moving at a certain speed and you have a certain amount of mass. That means you have a certain amount of kinetic energy. So now you have that much ability to do work on something else. Is that much kinetic energy that you actually have. All right. So let's do a little practice problem. All right. So Dalvin Cook, if you did not know this, Dalvin Cook is actually one of the fastest. Actually been clocked as probably the fastest person in the NFL on a test that they did. I think they did in 2018, maybe 2019 was the test. Okay. So he's been clocked at a top speed of 9.84 meters per second, which is 22 miles an hour. That's incredibly fast for a runner. He has a mass of 209 pounds, which is 94.8 kilograms. So we want to make sure we're in meters per second and kilograms for our mass. These are just here to reference to like maybe more your common knowledge of what this guy can do. So how much kinetic energy does he contain at top speed? All right. So as always, let's pause the video, let's work it out, and then we'll come back for a solution. Okay, so here's our solution, right? So we know here's our equation. We plug in the mass of him, which is 94.8 kilograms, take it times his top speed of 9.84 squared, and he can output 4,590 joules of kinetic energy, or he's using, I should say not output, using 4,590 joules of energy as he is running at top speed. Okay, so all of this energy is being used to do work on his own body, okay, because he provides a lot of force to carry him through a distance, because obviously as he's moving, he's going to be traveling a certain amount of displacement or distance there, okay? So we actually could track how much force he outputs over, let's say, a 40-yard dash if we knew that, because we know the energy, so we could actually figure that out also if we wanted to as a follow-up question here, okay? Now, the other type of energy we want to talk about is gravitational potential energy, okay? So this is a potential energy that comes from gravity, right? We'll do elastic stuff in a different unit. So right now we're only going to focus on what happens for potential energy, or this potential because of your height, all right? Height above the 0 point or the surface of the earth, whatever we count as 0, okay? So basically, if it's gravitational, it's your energy based off height, okay? Two things. Now it's based off mass, because mass is always part of energy in terms of solving for it. And then it's also how high up you are. Again, the more massive you are, the more potential you have. Okay? Think about this. If you stored a bowling ball on a shelf above your head, or a ping pong ball, okay, which one would you be more worried about falling on your head, right? Probably the bowling ball, because it has more mass, because it has more potential to hurt you. Okay? So we say things that have the potential to hurt are things that have the more potential energy in them, right? Height, the higher up you go, also, okay? Would you care if you stored, let's say, a baseball 2 foot above your head? I mean, if it fell down and hit you 2 foot above your head, it probably wouldn't feel great, be fine. But what if you stored it 10 stories above your head, okay? There's a lot more potential for pain if a baseball fell 10 stories and cracked you in the head, okay? So those two things are our two variables here in terms of what we have. The higher up they are, or the more massive they are, okay? Now, if you notice, this equation is not new to us, all right? We've already talked about the mass times the acceleration due to gravity times the height being something that is the work done to lift something. Well, if you're going to put work in to lift something, that means you are giving it potential energy, or you're raising it above a surface. So the work you put in, you actually gain potential energy by doing that, okay? So when you lift something off the ground, it takes work to do that because you're putting it into this potential energy, all right? So again, our energy is joules, mass is kilogram, and our height is in meters here. And G is the same as we've always been using, that 9.81. Now keep in mind, you're going to use it as a positive 9.81 here because as we raise things up and give it more potential energy, we're actually lifting it or we're opposing the acceleration due to gravity. So it's a plus number here and not a negative number here. Okay? Okay, so let's do another practice problem now for potential energy. All right. So after scoring a touchdown, the team lift Dalvin Cook off the ground, raising him 1.5 meters into the air. How has his gravitational potential energy increased? Okay, so we know how high we lifted him. We remember his mass is 94.8 kilograms from previous problem. So what is his new gravitational potential energy? Okay, pause it here, and then we'll get to a solution. All right, so here's our solution. If we take our potential gravitational energy here, and we have his mass here, the acceleration due to gravity was as a positive value, 9.81 here, because we're lifting it up. We're opposing gravity here. A height of 1.5 meters. We gained 1,390 joules of potential energy by raising him 1.5 meters into the air. Okay. Now keep in mind that if you know the work you put in or the potential energy, you could always solve for how high up you got something and also the mass too. So we could be rearranging these equations. Just for our first practice problems here in the video lesson, we're not doing any mathematical rearrangements of these. Okay.